of your pod. Whether it's for scale, to meet more demand, or for reliability, to have backup workers in case one or many die, replication is an important cornerstone of Kubernetes. Kubernetes supports scaling through replicating pods on the same or multiple nodes. But before we go into how this works, let's explore how applications should be designed to scale in Kubernetes. Many paradigms exist for effectively scaling an application. For our purposes here, we'll categorize them into stateful and stateless applications. Stateful applications store client data generated in one session for use in the next session with that client locally. The effect of this is to essentially lock a client session to a given thread or instance of an application on the server. If that server process dies, client state is lost. It is also the only one who knows what state that user's data is in. All subsequent requests must come to it. Stateless applications, on the other hand, update a centralized data store, such as a database with the result of a single operation, so the next client session or operation can be handled by any thread or instance of the application. Kubernetes supports both patterns. However, it is a best practice to create stateless applications whenever possible, and leverage replication without having to use stateful replication mechanisms. Architecting applications varies by programming language and framework, and it's beyond the scope of Kubernetes. Many great resources on software design exist that discuss the different approaches to designing stateful or stateless applications. For now, let's assume you're working with a stateless application so we can focus on how Kubernetes handles scaling through replication. Kubernetes gives you a variety of options to define how a pod should scale. By far the most robust, flexible, and frequently used is setting the replica options in your deployment. It's what we'll do today. Just for the record and for your knowledge, you can also define a replica set, deploy multiple bare pods, define a job. This is useful if you're doing a niche form of bash processing, or a daemon set if you're looking to replicate older software patterns like daemons. However, the dominant way of deploying a replica is to define the replica options in your deployment, and that's what we'll do today. We'll focus on the first as it's the most common, robust, and useful. Don't worry about the details of the others. We only mention them to be complete as you may encounter them in documentation, discussions with others, or elsewhere as you explore Kubernetes and need to address more advanced niche use cases. Let's look at something familiar, our Tomcat server from previous lectures. Remember our Tomcat server deployment and when we said that we'd come revisit a few of the other parameters? Well, let's example the line that says replicas 1. At the most basic level, this is where we declare to Kubernetes how many copies of the pod we'd like to run. We can run as many as we have resources for on our cluster. There are various other properties we can set to define how these replicas are built, where they run, and the like. But for now, let's keep it simple and simply tell Kubernetes we'd like to run 4 replicas and leave the rest to Kubernetes itself. By setting replicas to 4, we have specified for this deployment that we'll have 4 replicas of the Tomcat pod running. This can provide redundancy and more capacity in a properly architected application. We could either create an entirely new deployment that looks like the above, or we could use a Kubernetes scale command to scale our existing deployment. Let's look at that. Issuing this command to our existing Kubernetes deployment modifies the deployment to have the exact same effect as if we were to make a new deployment, but it saved us from the headache of having to delete our old deployment and create a new one. It's also avoided any downtime for the application during that switchover. The kubectl scale command will set our existing Tomcat deployment to 4 replicas. Let's run this against our existing Kubernetes deployment and see what it does. If you had stopped Minikube the last time you'd used it, remember to start Minikube by issuing the minikube --start command. I already have it running, so I won't execute it. Let's use the kubectl scale command. Let's type kubectl scale --replicas equals 4 deployment / tomcat -deployment. Let's execute the command to scale our Tomcat deployment to 4 replicas. At this point, you can trust that Kubernetes has scaled the Tomcat deployment given the output from the command. Or you could use a number of commands which you're already familiar with. For example, the kubectl git deployment command will get the information about the Tomcat deployment. You can see here we successfully have 4 up-to-date replicas. You could also use the kubectl describe deployments command to get more detailed information about the nature of these 4 replicas. You can see from the output of this command that Tomcat deployment was scaled to 4 of 4 replicas just a few seconds ago. So, now that Kubernetes is running 4 replicas, how does it decide which one gets to do the work? That's the second half of scaling. Now that we have 4 replicas running, we'll need to update our service definition connected to our deployment to take advantage of our replicas. You may recall from previous lectures that the only way pods can be exposed to the outside world is through defined services. We have used the kubectl expose command to create services to expose our previous Tomcat deployment to the outside world using the node port service. This command created an external port that connected to the port running on the pod that ran the Tomcat container. It mapped one port to one service on a node. That's what a node port service does. Now that we have multiple nodes running the same service, we need to graduate to something that can handle something more sophisticated than just exposing a single port on a single node. You may recall from the previous lecture that the load balancer service provides exactly this function. A load balancer is a type of service that exposes a single port, but uses a variety of internal logic, which we'll cover later, to decide which replica to send the request to. Let's look at what a load balancer service will look like for our Tomcat replicas. As you can see, it's not that different. We've added a few more options to set the newly created service's name to something predictable, and define the port we'd like to listen on and what port it's going to be on the pod. First, let's use the kubectl expose deployment command. Using this command, we will specify that our Tomcat deployment should have a load balancer exposed on port 8080, forwarding to port 8080 on its container and all its replicas, and we'll give it a name, something that we can easily refer to it by later. We'll see the command is successful when we can see that the service was properly exposed. Finally, we can use the kubectl describe services command to give us more information about the newly created service. Specifically, we can see what IP address was issued for the newly created load balancer. Let's issue the kubectl describe service tomcat-load balancer command. Remember, that's the name we gave it when we created it. As you can see, it's assigned an internal IP. Since we're running on Minikube, this will be an IP that we probably can't access. When running on a production cluster, it will be available as an external IP from whatever APIs your cloud provider may provide. For now, let's not worry about how we access the load balancer. We'll get into that when we talk about the DNS system and how names and network addresses are resolved in your Kubernetes cluster. For now, simply be confident that the load balancer was properly created, and since we're running on a mini